Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yi Tay, right? From Berkeley. He did his PhD with Jeff Hinton at the University of Toronto, and he's now working with Michael Jordan, David Forsyth, and Jitendra Malik at Berkeley on things related to machine learning and computer vision. One of the interesting things he did in his past life at Toronto was his work on contrastive divergences, and today he'll talk about hierarchical Dirichlet processes.
Thank you, Nematode. So the title is Hierarchical Dirichlet Processes, and there's kind of two terms in there, and they are both from Bayesian statistics. And they're kind of like two pillars of Bayesian statistics, which I'd like to just like tell you a little bit about before I start the talk. The first one is hierarchical models, and these are probabilistic models in which you actually model dependencies. So probabilistic models, they have variables, and then you have parameters which determine the distribution. And hierarchical models are models in which you actually put prior distributions on your parameters such that you actually have dependencies on your parameters. And what this does is that it allows you to share statistical strength between different parts of the model, and basically it makes the model more statistically efficient. The second term here is Dirichlet processes, and these are pretty standard non-parametric models by now. And they are basically an elegant Bayesian alternative to finite mixture models. And basically, these models can automatically determine the appropriate size to use depending on the data in a very efficient manner. And I'll show later that it's going to be much better than model selection. So I started working on this thing when I was looking at two recent models in machine learning, one called Latent Dirichlet Allocation and the other called Infinite Hidden Markov Model. And I'll go through them as kind of motivating examples as to why we want to work on hierarchical Dirichlet processes. So the first problem that we deal with is Latent Dirichlet Allocation. And the idea here is that we're going to model documents as topic models. That is, we're going to say that each document is kind of generated as a combination of topics, right? And the words kind of get associated with different topics. So here's an example. Suppose that we have a news document which looks like this. Then we could perhaps say that, this document is about, say, 4 different topics. The first topic is auto industry, another one on market economy, another one on US geography, and another one on just plain old English. And the idea is that each document now is a different combination of different topics. So we could have, and then each topic is a different combination of words. So basically, for example, the auto industry topic consists of words like Nissan, cars, and trucks, and vehicles, right? And then each topic is also shared across multiple documents. So why do we want to do this? Well, I'll skip to this one for now. The idea is that if we have a bunch of training documents, and we are able to kind of discover the various topics which occur in this training corpus, and we're given some test document, then we can do some sort of summarization of what this test document is about by saying which are the topics which occurred in this test document. So I think Dave Bly et al. Have come up with a model for describing topics and documents called the Latent Dirichlet Allocation. And the generative model is as follows. So I guess this is the graphical model for LDA. For those of you who don't know, the circles are basically variables, and the edges here describe dependencies among your variables. And the rectangles describe plates, which are basically replicating of variables. So the idea here is let me see. So the outer plate here is describes documents, okay, and each document has a number of words given by X, okay? And we generate the words in the following way. We first generate the topic which this word comes from, and then given this topic, we can generate what word is the identity of this word from the distribution given by the parameters of the topics here. And the documents here contain mixing proportions, which basically describe which combination of topics appear in that document. And these mixing proportions are basically sampled from a Dirichlet distribution. Actually, it's a flat Dirichlet with some parameters alpha over k. So when Dirichlet came up with this model, the number of topics that appears in your training in your documents is actually has to be specified by the user, and we would like to have a model which can actually automatically determine the appropriate number of topics which appear in the training document. Okay, so that's kind of one reason why we would want to use non-parametric models. We'd like to determine the appropriate number of topics efficiently. And the other thing which is important about LDA is that the topics are actually shared across multiple documents. And why do we want to do this? Well, first of all, there's a lot of sharing of statistical strength between documents. So if we have a topic which appears in two documents, then both documents can kind of contribute to to the model figuring out what exactly is this topic, right? And of course, it also allows generalization to new documents, in that, you know, if you're given a new document, test document, you can figure out which topics appear in this new test document from your training documents. So there's kind of two requirements here. One is you want to determine the number of topics efficiently. The other one is you want to make sure that topics are actually able to be shared across documents. The second model which I looked at and kind of like helped in motivating this hierarchical Dirichlet process is called the infinite hidden Markov model proposed by Matt Bill. I guess if you don't, if you're not familiar with this, then I'll describe it a little bit, I guess. So it's a hidden Markov model which actually can automatically determine, again, the number of hidden states efficiently. And the idea is that you're going to construct a hidden Markov model which can potentially have an infinite number of states. Okay. Now, given any finite observation sequence, if you can now compute the posterior over the hidden states, then you only use a finite number out of this infinite number of hidden states. And that number of states tells you how many hidden states is actually appeared in your data. But it turns out that there's a tricky business in that if you just use the normal hidden Markov model or way of describing priors and distribution over hidden states and distribution over observations, then what happens is that the hidden Markov model would actually, the infinite hidden Markov model will actually screw up, in that what would happen is you would always, once you get into a new state which you have not observed before, then you always go to a newer state and a newer state, right? So so the model becomes a trivial model, which is basically a left-to-right model. And the way they solve this problem is to actually introduce an oracle which ties together the transitions in the hidden Markov model. And the idea is the following: suppose that I'm just going to describe the generative process for the infinite hidden Markov model. Suppose that you've generated a number of hidden states up to Vt, and suppose that the value of Vt that you've generated is I. Okay. Now you can look at what is the probability that Vt plus 1 is going to be equal. So you have to look at what's the generative process for Vt plus 1 given Vt. Okay. The probability that Vt plus 1 is going to equal to some previously seen state, j, is going to be proportional to Nij, which is the number of times you've seen the transition ij. And with probability proportional to alpha, you're going to call an oracle. And this oracle is going to say that you either generate a new state with probability proportional to gamma, or you go back to a previously seen state j with probability proportional to the number of times that the oracle chose that state. So this generative process is kind of is very complicated, yes. And it turns out that because of this, they didn't actually propose an exact inference algorithm for this. Well, actually, they proposed a heuristic of 2-bit sampling. So I started working on hierarchical Dirichlet processes to solve the two problems that I just described. First of all, to kind of make better sense of what this thing means. And second of all, to actually have a equivalent and infinite, a non-parametric version of LDA, which can automatically determine the number of topics in my documents. So I'll talk about hierarchical Dirichlet processes here. Any questions so far? Yes. LDA is, I guess, a probabilistic version of latent semantic analysis. Oh, yeah, that's right. I think that's different, even though I've not actually read that paper. One thing. Oh, to probabilistic policy. Oh, I see. Okay. I should check that out. So, I'll first describe kind of the general framework for hierarchical Dirichlet processes, or HDPs. We are going to assume that our data consists of j subgroups of data. So in the document modeling application, each document the words in each document you can assume to be one group of data. Okay. And let's just say that group J consists of nj observations, xj1 until xjnj. And we're going to assume exchangeability. And what that means is that basically the ordering in which the data comes in actually doesn't matter, which is a standard assumption in latent semantic analysis and latent Dirichlet allocation. And this assumption, in that context, is called the back-of-words assumption. Right? And this exchangeability assumption, of course, will make us lose relationships between data items in each group. But we gain simplicity in modeling these groups of data. So, and our contribution is going to be, basically, we use non-parametric models and we use hierarchical models. The non-parametric part of the model is going to allow us to determine the number of components or the number of topics, and the hierarchical model part of the model is going to allow us to share the components or the topics across the different groups. So, right. So before I go on to hierarchical Dirichlet processes, I need to kind of give you a bit of detail on Dirichlet processes themselves, because they are kind of a bit, perhaps, if you're unfamiliar with them, it might be a bit complicated. So a Dirichlet process, by definition, is a distribution over distribution. Okay? And we say that a random probability distribution G is distributed according to a Dirichlet process with parameters alpha 0 and G0, where G0 we call a base distribution for G, and alpha 0 we call a concentration parameter or a scaling parameter. And the idea is that G0 is going to act like a mean for G, and alpha 0 is going to describe the amount of variability around G0 that our random distribution has around G, around its mean. Okay. And in Dirichlet process mixture model, we model each data item xi in the following way. So since G itself, so we first sample G, right, from the Dirichlet process. And then since G itself is a distribution, we can obtain samples from G itself. And these are called phi I, say. And then given the phi i's, the x's are just generated from some distribution parameterized by phi I. Okay, so the graphical model is shown here. And this is called a Dirichlet process mixture model. You might want to ask, why is it called a mixture model? Because it doesn't seem that there's, mixing components or clusters involved. And this clustering appears in the definition of the Dirichlet process itself. So actually, I'll skip the definition of the Dirichlet process, the actual definition of the Dirichlet process. So I think the first paper on Dirichlet processes came out in 73. But the definition of Dirichlet processes given there is actually not very helpful because it's kind of an existential definition. It's not a constructive definition. And I'll just go on to the next definition of a Dirichlet process, which is a lot more constructive, and it actually tells you exactly what are the Dirichlet processes. So why is the DP mixture model called a mixture model? So there's this construction by Soto-Roman, which basically shows that any sample from a Dirichlet process always has a form given by an infinite sum of delta functions. Okay? And this beta k's are basically weights on our delta function, and delta functions are basically distributions which puts all its mass on one point. Okay? So here's kind of a visualization of a sample from a Dirichlet process. It's basically just a bunch of delta functions, and then the height of the bars here describe the beta k weights. Okay? And of course, the beta k's have to be non-negative and they sum to 1 because G is a random distribution, so it has to have a total mass of 1. Right? So why is this called a stick-breaking construction? The metaphor is as follows. We're going to take a stick of length 1, and the length of the stick is going to represent the mass of our distribution. We're going to break off one piece of the stick and stick it somewhere. Okay? That's going to be our first term in this sum. And then we take what's left of the stick, and then we're going to break off another chunk and then stick it somewhere else. And that's going to be our second term in that infinite sum. And then we're going to continue breaking off smaller and smaller pieces of the stick and kind of put it around our space. Right? And that's what we get here. And that's why this is called a stick-breaking construction. And basically what Soto-Roman showed is that if the beta k's satisfy a certain sample in a certain way, and the theta k's are samples from G0, which are basically IID distributed, then if you construct G this way, then it would always be a sample from a Dirichlet process with those two parameters, alpha naught and G naught. So what does that mean? This means that if you now generate a sample from G, and since G is an infinite sum of delta functions, our samples from G phi I is going to be equal to one of the theta k's with probability equal to beta k. Right? So what that means is that we can associate each theta k with a mixture component, and this model is going to be a mixture model with an infinite number of mixture components. Right? So I guess that's pretty simple. And kind of this Dirichlet process mixture model as an infinite mixture model has been kind of like worked on by a variety of people, including Vector Neal and Carl Rasmussen. So let's just imagine using Dirichlet process mixture models for our setting of grouped data. We can model each group of data with a DP mixture model. And if we do that, then of course each group can automatically determine the appropriate number of components. I kind of forgot to mention something. So the DP mixture model has an infinite number of components, right? But let's just see what happens when we only observe a finite number of samples from this model. So basically a finite number of xi's here. What happens is that because we only have n samples here, the maximum number of mixture components we can observe in the posterior is n, right? And in fact, if you actually look at the posterior of this thing, the number of components used to generate our data x is actually typically much less than n. And the number of, and that number basically tells us the number of components we should use to model our data. Okay? And that's a random number as well. So, right, so we model, so we put a plate around the inside here where the GJs are Dirichlet process distributed according to the same hyperparameters alpha naught and G naught. And then we're going to model each group of data with a Dirichlet process mixture model. So we generate our samples from GJ, and then we generate our data given the 5 JIs, right? So what happens here is that each group can now actually automatically determine the appropriate number of components to use. But what's the problem here? The problem is that we're actually modeling each group of data independently, right? So these are hyperparameters we assume to be kept fixed. And of course, since this is a graphical model, and all of us know that all the groups are basically conditionally independent given alpha naught and G naught. So the groups are modeled independently. And is that actually useful? It turns out that it's actually totally not useful, because let's just imagine that G naught is continuous, which is quite a standard assumption, I guess. So Gaussians or Dirichlets, they're all continuous distributions. And if G naught is continuous, and we construct two samples from our Dirichlet process, say Gj equals to 1 and Gj equals to 2. Okay. We construct two samples like this, and the locations of the spikes are sampled from G naught itself. Right? And since G naught is continuous, the set of spikes which appear here and the set of spikes which appear here are never going to overlap. And what that means is that the components used here are never the same as the components used here. That's kind of easy to see. And so in the language of topic modeling, that's kind of saying that the way we're going to generate our data is that documents are never going to share topics, and that's totally useless as a topic model, right? So what do we do? So see kind of a bit of difference in the graphical model. You mean G naught here?
Yeah.
Well, for example, in the topic model, you typically say that topics are multinomial distributions. So the parameters of this multinomial distribution lie in this k-dimensional or n-dimensional simplex or something, right? And the Dirichlet distribution on this n-dimensional simplex is a very natural prior to use, and that's continuous. But as a matter of fact, what we do in the hierarchical Dirichlet process is to say that we don't want G naught to be continuous. We want it to be discrete, because once G naught is discrete, and we sample kind of sticks from here, they are forced to actually line up, right? And which is exactly what we do here. So once you have G naught being discrete, what is a natural prior to use for G naught? Because a discrete distribution is very complex. You need to make sure that you put an appropriate prior over them so that when you compute the posterior, it makes sense. Right? So the most simple prior we could think of is, again, to use Dirichlet processes. So we say that G naught itself is going to be Dirichlet process distributed with some other hyperparameters, gamma and h. Okay, so h is going to be our global base distribution now, and gamma is going to be a scalar, a concentration parameter for G naught. And then given G naught, each of the GJs is now going to, again, be a Dirichlet process with parameters alpha naught and G naught. And that's basically the hierarchical Dirichlet process. It's kind of simple. It's a simple, it looks to be a simple model. You just generate G0 and then generate Gj, and they're all Dirichlet processes. Okay. And if you now kind of append this bit of it to the model, where you generate samples from Gj, and then you generate words or observations from these parameters, then we get the hierarchical Dirichlet process mixture model, or I just call it HDP mixture for short. So that's the hierarchical Dirichlet process mixture. Do you have any questions so far? Pretty easy. So let's look at let's try to understand what happens in this model, and by understanding kind of what does G0 look like and what does Gj look like, we can then actually construct inference algorithms for sampling from the posterior. Since we just said that Gj is a sample from a Dirichlet process, we know that it has a form given by this, where the theta k's are samples from H, and the beta k's are constructed by this kind of breaking off the states idea, right? And that's given by that bit here. And the Gj is of course also a sample from a Dirichlet process, so we can write it as an infinite sum as well, where the delta functions are actually located where are actually sampled from G0, right? And because G0 is discrete, any sample from G0 is going to be equal to one of the theta k's. So we can actually write the individual Gk's as again an infinite sum of delta functions with the same locations, theta k, but the difference is that the pi jk's are different from each other and from beta k. As a matter of fact, what you could show is that the theta k's are IID samples from H. The beta here is going to be constructed from a stick breaking construction, and the pi j's are going to be some sort of distribution which depend on beta, and the dependency looks exactly like this. So you can see the similarity between this model and this model. So this is G0 and this is Gj. Okay. So what does this mean? This means that the HDP mixture model is simply an infinite mixture model where the components are given by theta k, and the mixing proportions, which correspond to each group of data, are dependent on each other through this dependence on beta. Right? Because beta is random, that introduces dependencies on our mixing proportions. And this dependence is actually going to allow the mixing components to be shared across groups. They are shared already because we are using the same set of theta k's here. Right, so to visualize this, what happens is, okay, so the red line here is H. So this is for Gaussian. And G0 is an infinite sum of delta functions. And each of the individual Gj's is also an infinite sum of delta functions, except that the locations here match the locations here, and the heights of the stakes depend on the heights of the stakes up here. So that's kind of the stake breaking construction. So that's kind of the HDP mixture model that I just described. And if we just put it side by side to the LDA model, then you can see the relationship between the two models. First of all, LDA is finite, and the HDP is infinite. Okay. And second of all, in the LDA, we assume that the mixing proportions are Dirichlet distributed with symmetric weights given by a constant alpha. While in the HDP, the pi j's are skewed, Dirichlet distributed. Actually, I haven't shown that they are Dirichlet distributed, but in fact they are. They are Dirichlet distributed with weights given by alpha naught times beta. and then we have a higher level prior on data given by the state breaking construction. So we can apply LDA to a set of documents and obtain a set of topics out. And we can apply HDP to exactly the same set of documents. And we can also get out a set of topics. And in fact, because this is a non-parametric model, in inference we actually get also a posterior over the number of topics, okay, that we should use. So we applied both LDA and HDP mixture to nematode biology abstracts. And a set of abstracts, I guess. And there's about 5,000 abstracts. And the vocabulary size, after pruning loud stop words and stuff, consists of about 5,000 words as well. And there's a total of about 500,000 words in total. So these are kind of two examples of abstracts here. I don't understand any single word here. But you can get this data set from the web as free. So you apply LDA. So I apply LDA to this thing. And of course, since we need to tell LDA how many number of topics to use, we tried it over between 10 and 120 topics. Okay. And each point here is the perplexity that LDA gives you for that number of topics. And you can have this kind of nice U-shaped curve, which basically says that it's overfitting here and it's underfitting there. And you should use a number of topics between 50 and 80. Okay. And if you now apply HDP to this data set, it gives you a perplexity which is right here, right at the bottom of this value. And the number of topics that it says you should use is between 60 and 70, so basically right in the middle here. So what does this mean? This means that if we use the HDP mixture model in place of LDA, then we don't have to worry about figuring out the number of topics to use. In fact, it took us like one run of HDP actually cost us about as much computation time as one run of LDA. So LDA is actually a lot more expensive. So the finite model is actually a lot more expensive than the infinite model in this case. Okay. And I guess the take-home message is, if you want to do any mixture modeling, you might as well just use a non-parametric model because it's so much simpler, so much less worries. Yeah. So I've described the HDP. Yes. Right. It's basically just git sampling. So what I do exactly is actually that I integrate out theta because it's conjugate, H is conjugate to F here. And I integrate out this thing because again a Dirichlet and multinomial are conjugate. And then I just git sample the Z's and the betas. And also I also put priors over these two things and then sample over those as well. And I do the same for LDAs, just to make sure that they're on par. Yes. 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 It's okay. It's a bit tricky because once you integrate out this thing, you're going to get a whole bunch of gamma functions, right? That's what you're concerned about. Sorry? Alright, okay. So the way I do it is you have a set of topics which are actually represented in the data, and then you always have a new topic. You kind of lump out. So that's right. So I kind of represent, so there's an infinite number of topics here, a finite number of which is used by the data, and I represent those separately. And then there's an infinite number of topics out there which is not associated with data, right? So what I do is you actually collapse them all into one topic, okay, which is sampled from the prior. And then this topic also has a certain probability of being chosen So when you give sample Z, there's always a probability that you're going to choose a new topic. And when you choose a new topic, yes, that's right. It's essentially uniform. Yeah. Yeah, so when you have a large vocabulary size, then that might not work very well. It seems to work fine here, but then you could get into details about what sort of Markov chains should you construct to make it mix better, I guess. So I don't know, split and merge, things like that. Okay, so this is actually avoids the need to do a reversible jump MCMC. It does something, quite similar, except that the space is actually fixed. It's an infinite space, but it's fixed, and you could do it. Of terminology. Right. Yeah. It's kind of like because of the prior you use on the mixing proportions, the sampling steps are actually, I think, quite a lot simpler. So I can only say that it's simple. All right, I see. Also, you're kind of proposing that, how would reversible jump MCMC look like in this model? I don't know, actually. I've never tried to use it here. Although, I guess if you read the literature, like I think Radford Neil has a tech report on MCMC sampling for Dirichlet process mixture models, and all the methods he used there are not reversible jump MCMC. So I kind of get the idea that it's probably not worthwhile to pursue that direction. Radford's always right somehow. So I talked about HDP and kind of this notion of a hierarchical Dirichlet process as a distribution over distributions, and I also talked about state breaking construction. And in this part, I'm going to relate it to the infinite hidden Markov model. So let's go back to a Dirichlet process again, and let's just consider obtaining a set of samples, say phi 1 until phi n, from G, where G is a sample from a Dirichlet process, so with parameters alpha naught and G naught. And let's just consider integrating out G and look at the conditional distributions of phi I given phi 1 until phi I minus 1. Okay, so we're going to generate, we're going to kind of integrate out G, and then we're going to generate the phi I's incrementally one at a time, and look at what do the conditional distributions look like. It turns out that they look very simple. They look like the following. There's always going to be a positive probability that phi I is going to equal to some previously seen value of the phi's here, and the probability that it's going to equal to a value psi t is just going to be the number of times that psi t occurred in the list phi I 1 until phi I minus 1. And there's also always a positive probability proportional to alpha naught that phi I is going to be a sample from G naught. So the idea is the following. I take phi 1, and that's going to, and I generate a sample for phi 1, and that's going to be psi 1 here, right? So, and then I generate phi 2, it can be equal to a new kind of table, a new psi, or it can be equal to an old one. And in this case, I chose to be the old one. And then you kind of like, and then for phi 3, you can generate from this conditional distribution. and it can equal to an old one or a new one. In this case, it chose a new one. Okay. And then phi 4, it chose an old one, and then 5, it chose a new one and a new one. Okay. So that's kind of the generative process that you think about, and that's the conditional distribution. And this clustering induced on the phi's is called a Chinese restaurant process. And you can do this for, in the case of the hierarchical Dirichlet process, we can do this clustering for group 1, and you can do this clustering for group 2, right? Where the size are now basically samples from G0. And since we know that G0 itself is a sample from a Dirichlet process, we can do this clustering on this set of samples itself. So that kind of looks like this. So each of the size now is going to be a sample from G0, and we can integrate out G0, and then we can look at the conditional distribution of generating the first size, the second size, the third size incrementally. And that's again going to look like a Chinese restaurant process, and I've kind of described the clustering of the size up here in this way, where the clusters are now the betas, and those are samples from H, and the probability that one of this size is going to equal to, so when you sample one of this size, the probability that it's going to equal to a previously seen value of theta is going to be proportional to the number of times that theta has been used previously, and the probability that this new size is going to equal to a new theta is going to be proportional to gamma. Okay. And how is this related to the infinite HMM? So what I've just described is, for each group, when you generate a new phi, for each group, the probability that this new phi is going to equal to some previously seen value is going to be proportional to Nik. And the probability that it's going to come from a new value of psi, a new value here, is going to be proportional to alpha. And when you generate if you generate a new psi, then you kind of go up to this level. So I don't have a kind of animated thing, but what you see is if you have a new value of phi, then this new value of phi, it can point to one of these old ones, old circles here, or it can point to a new circle. If it points to a new circle, we now need to generate where does this circle point to. Right? You can point to an old circle up here, or you can point to a new circle. So this bit is when the new point points to an old circle. This is when it points to a new circle. And if you point to a new circle, you now want to figure out where does this circle point to. And it points to an old circle up here with probability proportional to the number of times that circle has been used. And that the probability that you're going to point to a totally new circle up there is going to be proportional to gamma. Right? So you can kind of put this to the generative process for the infinite HMM side by side, and you can see basically that the oracle that they use in the infinite HMM basically corresponds to this part of it, where it basically corresponds to the higher level Dirichlet process. So kind of we can work backwards and say, what is the hierarchical model which corresponds to the infinite HMM? And that basically looks like this, where the thetas are basically parameters for the transmission probabilities. So theta k is the transmission probability for hidden state k, and emission probabilities. And the transition probabilities are given by pi k. So pi k is the transition probability coming out from state k. And we're going to introduce dependencies among the transition probabilities by saying that they're going to be Dirichlet distributed with a mean of beta. And this beta itself is going to be a Dirichlet distributed or actually it's going to be a stick breaking, constructed using a stick breaking construction. Right. And that's basically the hierarchical Bayesian model, which corresponds to the infinite Sherman. And I guess the idea here is that this is a much cleaner formulation, much more understandable formulation than something which looks like this, which is kind of, you look at this and you're like, okay, how do I do sampling in this thing? Yeah, that's too complicated. But once you have a model which looks like this, it's now easy to construct a sampler for the infinite Sherman. And you can, again, do the same thing. What I do is I just do Gibbs sampling. I integrate out this variable and that variable. I sample this by Gibbs sample, and I sample beta given the hidden states. That's easy. So again, we can compare. So finally, we actually have a sampler for the infinite Sherman, and we can compare the infinite Sherman versus other methods. And in this graph, I've shown the perplexity of the infinite Sherman, the perplexity of various methods here, and I compared the infinite HMM, which is down here, that's the perplexity, so lower is better, against 3 other methods, maximum likelihood, which goes up here, map estimate, which is the red line, which is the green line, and VB, which is the red line. And basically what this graph says is that the infinite Sherman just outdoes all the other methods that people have come up with for HMM learning. We've not compared it to Stokey and Omohundo's method yet.
But the best number of states for the other together?
So on the x-axis here is the number of states that the other model uses. Yeah, because all these other models are finite models, so you need to tell it the number of hidden states to use. But with the infinite hidden model, it just determines that automatically. I don't remember how many states does it use though. Yes. Perplexity is exponential. I can write it down. Intuitively, it means kind of the equivalent dictionary size. If the equivalence it's the equivalence dictionary size if you assume that the model is uniform. Right. So it's kind of saying, on average, how many words do you need to figure out what's the correct word? So in this case, it would be about 10. So I've I've shown you an example of using hierarchical, of using HDP in infinite Sherman, and I've shown you comparing HDP mixture models versus LDA. And in the last part of the talk, I'll talk about an application for NIPS papers. So the NIPS corpus which we use consists of NIPS 1 until NIPS 12, and we take all the NIPS papers in those 12 years, and we put them into 9 possible sections, given by these 9 prototypical sections here. We have cognitive science, neuroscience, learning theory, AA, implementations. Yeah. There are kind of different sections in NIPS, and they talk about different things. So neuroscience versus AA, for example, have 2 different ends of the pole. And I've kind of described to you some statistics, I guess. The number of papers here, AA is of course by far the largest, and cognitive science is smallest. And the number of words and distinct words and things like that. Again, I've pruned away a lot of the stop words, so that the total number of distinct words is about 5,000. And what do I want to do with this thing? What I want to do is that I'm going to treat each of these sections as a separate corpus of documents. And I'm going to ask the question, suppose that I want to model vision sciences papers, okay? And I have some training data and I have some test data for vision science. And then I can look at how well does the model do, okay? And then I can ask, what happens if I give the model one additional section, say the AA section, right? How much better can it do with this additional information from AA. So the idea is, yeah, so I've just described this thing. I have a training set which consists of training documents from Vision, and I want to test on some documents in Vision which is not in the training set. So I'm going to look at the perplexity of these test documents. And also, I'm going to give the model an additional section, papers from an additional section, and look at whether adding this additional section will actually help in the training of the model. Yes. Well, the idea is that even though this is a different section, it still gives you a lot of information about which words occur more frequently than other words. And depending on whether this section is closer to Vision or not, that's going to actually give you a different amount of transferring of information, right? So if you think, yeah, that's right. Yeah, that's right. So if you have more topics which are shared between this other section and the Vision section, then this transferring of information should be better. And if there's less, then there's going to be less transferring. Right, so that's I'm going to come to the models to use here. So different models will use this additional section in a different manner. Right? So the first model is just to ignore the additional section. I'm just going to look at the training documents from Vision and test on Vision. Okay? And this is just a hierarchical Dirichlet process. These are the groups. That's the base distribution. The second model, which I'm going to look at, actually just says that this additional training documents from the new section, I'm just going to lump them into the rest of the Vision documents. And this is again an HDP mixture model. But the problem here is that we know that this additional section is actually similar to but different from Vision. Right? So we actually really want to have a model which distinguishes this additional section from the Vision documents. So what we do is, we do it hierarchically. So this bit of the graph, including G2, G, and this bit, models our Vision section. Right, so you can think of the GJs as the mixing proportion over topics for individual documents, and G2 as the mixing proportion of topics for the Vision section itself, for the whole section. And I'm going to model this additional section with a different hierarchical Dirichlet process with its own mixing proportions. Right? And then in order to introduce dependencies across this section and Vision, I'm going to put one more I'm going to put one more layer into the hierarchy and say that both of these things are going to be Dirichlet processes with distributions with a base measure given by a global G0. Right. So this is kind of the most hierarchical model if you think of for this case. Or not really the most hierarchical. You can think of even more complicated models, but it's definitely a more reasonable model than the previous two models. Right. So you can now look at the perplexity results again. So if you ignore the additional section, you start off with really bad perplexity. Oh, sorry. On the x-axis here, you have the number of training documents in Vision that you use. Right. So as you increase here, the perplexity should decrease. You're always testing on the same set of test documents, but you vary the size of the training Vision documents. Yeah, so the number of documents you use in the additional section is always fixed. It's actually just one of them. I'm just using one additional section. Yeah, and I'm always using all of them. Right. So if you ignore the additional section, then of course you're going to start with a really bad perplexity. But this perplexity is going to reduce pretty quickly, and you're going to converge to here. Okay. So that's M1, which ignores the additional section. If you actually use M2, which is this model where you have where you just lump in the papers, the additional papers into the vision papers, what happens is that it does pretty well in the beginning because you have a lot more training data here. But after a while, it actually does worse than both of these models. And the reason is, of course, that the documents from this additional section is actually overwhelming the training data from vision itself. Right? So it's, of course, not doing as well as these other models. And if you look at the hierarchical model now, at zero training documents, we can just ignore this point. But really quickly, it actually does better than both of them because it can use information from the additional section and it uses information from the vision training documents. And it stays being the best down here because the papers from the additional section is not overwhelming the vision training documents. Right? So, and the reason is that we're basically modeling this part distinctly from that part. Okay. So, this basically shows that the hierarchical model is better. We can also look at which sections are closer to vision by looking at the perplexity. So here I'm kind of saying, okay, the blue curve is saying that I'm using learning theory papers as the additional papers. And that's the perplexity curve. And of course it does the worst because learning theory actually has not much to do with vision. And then I can look at AA papers. If I use AA papers as the additional papers, then it does better than learning theory. And then if you look at AP papers, which are applications, then of course it does the best because there are vision papers in the applications section itself. So you can see this very nice generalization ability from the most theory, from the furthest away from vision to the closest to vision. It's kind of a nice curve to see. You can also look at the topics which are shared between vision and the other NIPS sections. And it's quite interesting to see here, for example, let's see, so the topics that are shared between implementation section and the vision section. So implementation are things like VLSI and things like that. And you see, for example, that the second topic that is shared between implementations and vision are basically chips for, basically talk about chips for implementing vision algorithms, like VLSI chips, I think.
Each topic is a distribution over.
Yeah, so I'm just taking the most, I'm just looking at the words which occur most frequently in that topic distribution. So you can look at the topics which are shared between algorithms and architectures and vision. And there are, AA type of things, algorithms, tasks, approach, methods based on problems. You can look at the, which one is it?
The last one, the probably architecture, that's similar.
This one?
In the AA.
Oh, CMAR, yeah. Yeah, that's right. So here's an important topic. Yeah, it's actually, tangent distances and things like that. It's quite cool. And then, of course, the topics shared between AA and vision is very different from the topics shared between neuroscience and vision. So these are kind of like more machine vision type of topics, and these are more biological vision type of topics. Right? So cells and activities and response and neuron and things like that. So, yeah, so that's kind of the application. So I'll just conclude since I'm running out of time. So we introduced the notion of groups data, where data comes from different groups, and you have to model the groups separately and yet in a dependent fashion. And we propose HDP mixture models for groups data. And they are hierarchical models, and the hierarchical nature allows dependencies or relationships between groups we model. And they are also non-parametric models, in which the modeling capacity will change according to how much data you have. And HDPs provide a very rich framework in which to explore, I'm just reading this, powerful new ways of working with mixture models. There's a variety of things which you could work on kind of like directly. So can we relax assumptions of exchangeability? So, for example, the infinite HMM is one possible way of relaxing exchangeability by modeling the time series aspect of things. We can also relax what non-parametric processes to use. So the Dirichlet process is the simplest Bayesian is almost the simplest non-parametric model that is in this class of models. There are other models based on, basically they are called stick breaking processes. They are kind of a lot more general, and I think Neil Friedman also has his own different model for non-parametric processes, and we can explore those things. So I'd like to kind of emphasize two things. The first thing is that non-parametric models, even though they look a bit complicated, they have these infinities flying all over the place, they are actually very efficient to learn. So in this case, inference in HDPs is very efficient. So for finite models, the computation time per iteration of the model is the number of data points times the total number of components used. In an HDP mixture model, the computation per iteration is actually the number of data points times the number of components actually used by the data. Right? So which is, they are pretty similar basically. But of course, you have to realize that if you use finite models, you need to use model selection to determine the number of components to use, and that's going to add a huge amount of computation overhead to your training of the data. And of course, we've only explored the simplest MCMC sampling algorithms, and hopefully there's going to be more efficient samplers or approximate inference schemes out there, like variational or EP type of things. So I guess the question is, why stick to finite models? I think everybody should go non-parametric at this point. The second thing that I'd like to emphasize is hierarchical models. So in machine learning, so there's this kind of well-known set of tasks in machine learning nowadays, variously called multitask learning or learning to learn. And the idea is that you have a number of different problems, and these problems all have their own set of parameters, right? And these parameters, given input, it produces the output, say. And these problems are all independent, are all different problems, but they are related in some way, which is why we want to do learning to learn. We want to generalize from old problems to new problems. And hierarchical Bayesian models are basically a very principled solution to this problem of learning to learn, by saying that our parameters is going to come from some prior distribution P, and if you now put a distribution over P itself, the fact that P now becomes random actually introduces dependencies in our parameters here, right? Because, yeah. And this dependency would actually allow us to do generalization to new problems and across the different problems. Yeah. So I've talked about hierarchical and non-parametric. And the last thing which I'd like to talk about is, which I'm quite excited about, coming here, talking to like David Heckerman and stuff, is soft parameter tying in graphical models. So in graphical models, let's just say that we have a Bayesian network in which we have a variable y, which depends on x1 and x2, and this is kind of the CPT associated with y for different values of its inputs. Right? And typically what people do is they just assume that the entries in this CPT are just Dirichlet distributed and they are all independent. So this is parameter independence assumption, right? And another case in which we have independent parameters is parameter modularity assumption. So in the case of, say, PER models or of PER models, we have, say, suppose that we have two variables and their attributes which belong to the same class, right? Then they would take the same inputs and they would have, typically what people do is they assume that the parameters for y is exactly the same as the parameters for z, right? Because that's the parameter tying that you do in PER models. And parameter modularity basically means that you either tie them together and say that these two things are equal, or you say that they're distinct and just independent. And with this hierarchical way of thinking about things, you actually don't want all these things to be independent. You want each of these things to be actually dependent on each other. So you could do that by saying that the common weights for the Dirichlet distribution should be random itself, so it's self-random, and then you can now construct inference algorithms over both the pi's and the betas, and that should introduce dependencies across the pi's. And this would help, for example, in smoothing out parameters when we don't have enough data. And the same here, if we have two pi's, again we want to introduce dependencies between the pi's without perhaps without saying that they are exactly equal to each other. So we can do that by again putting another hierarchy into the model and introduce dependencies among the pi's. So that's it. So, questions? I guess no questions. I actually treat them as all the same, actually. But I tend to think, in the machine learning perspective, I tend to think of parameters as things which as kind of variables as things which lie in the plates of your data items, and parameters as things which lie outside. But they're just the same thing. They're all random. Well, that's what we have in this grouped data case, right? So the GJs are kind of like parameters to the things for the inner plate, and they are variables for the outer plate. So.
Well, at some point you but it's certainly the highest level parameter is chosen, right? If not, at some point
Yeah, at some point you have to put in some numbers in there. Yeah, exactly. But the idea is that once you've gone far enough away from the data, and you don't have that many variables to put, it doesn't matter anymore. So in the HDP case, let me see. So in this case, I actually only have 3 numbers that I put in. Actually it's 4 numbers. So H, I assume to be symmetric, and so you have a weight that you want to give there. And then I actually integrate out alpha 1, alpha 0, and gamma. And they're gamma distributed, and with some hyperparameters. Yeah. So there's only very few numbers involved.
So how much influence do you find that, like in a lot of kinds of learning similar models like Allocation learning, not certain parameters, but with enough data, you can overwhelm the parameters.
Right.
Calculate somewhere. And I'm curious in this kind of thing. Let's say I start off with some, my fire on the distribution over components that is around 60 or something. But
Right.
I actually give it lots and lots of data that has activity around 80 clusters.
Right.
So do you see with more and more data that you actually,
Yeah, I think with more and more data, you would actually, the model should figure out, unless something goes wrong with the sampling, the model should figure out.
Yes.
Yes.
How strong is the effect of the prior here stronger in some sense than it would be?
Right, I see. So the model as it is here is actually quite sensitive to the settings of distance of the concentration parameters, which is why I integrate them out. Right, and once I integrate them out, the hyperpriors on which the concentration parameters rely on becomes less dependent on those things.
You integrate them out of all possible.
You can't do that. Well, because I'm doing sampling, I'm just sampling the concentration parameters as well. Yeah, that's right. I do find in this case that so H here is a symmetric Dirichlet with a particular weight, and this model is actually quite sensitive to that weight. We haven't tried sampling over that weight yet.
But if you have this, well, I mean, if you have this sample, you can
No, because it's not a double loop thing. In model selection, you're kind of varying. Yeah. You for each value of the concentration parameter, you do everything, right? But in this case, you're kind of wrapping everything in together. Yeah, that's right. Yeah, and the sampling for the concentration parameter is actually very cheap compared to the rest of it. I've not tried continuous data yet. I've done like simple Gaussian mixtures, right? And it kind of it works there, but I haven't really worked on any real application involving continuous data. It would be interesting if you have any ideas about what sort of things would be useful for this. Then I'll be delighted to hear. Okay. You could replay processing on the thing. Oh yeah, that's right. Right, I see. Yes. Different number of segments. Infinite number of segments. But you probably want to have a model which introduces dependencies among neighboring pixels. And that's kind of a bit unclear to how to do.
Well, the latest meta-analysis would actually work with that component.
Oh, I see.
So that's what Bucky is called.
Right. Oh, I see. Oh, right. Okay. That was UAI 2 years ago?
I saw that back in 2001, 2002.
Interesting. Right. Cool. I should check them out. Yes.
So this company is very productive
Mm-hmm.
The real life model
Right.
you have sensors because condition is really not so bad, but do you have any sense in whether it's mixing or what you think
Right. I do find that kind of mixing is actually a general problem with any sort of sampling for mixture models. But I guess my take on this thing is that you can say that Gibbs sampling doesn't mix properly, but say you do variational approximation, right, and that converges to something. But we know for sure that that convergence is to a local thing. Right, I see. I've not played with any of those things yet. I think I'm quite keen on doing split and merge type of ideas for mixture modeling. I think those are pretty good sampling techniques to use in this case. So, for mixture models. But I kind of have a practical bent on sampling. I think for the same amount of computation, sampling does just as well as variational approximation, or better. And if you're willing to spend more time on it, then it does better and better. That's what I think. But I guess you guys probably have a different Alright, yes, that's true. Actually, probably don't know about you guys. Yeah. Sorry? Oh, okay. Right, but if you cannot write that, then you can't do anything else. Right? Or you have to do like metropolis case or something like that. You can't do variational. Thank you. What's this? How do you escape?
not